It's my great honor to introduce our colleague, Professor Wai Lun Chan. I'm not sure that's necessary, but he graduated from Chinese University of Hong Kong in China, and then he got his PhD from Brown University. Then he did postdoc at UIUC and UT Austin before joining us as a assistant professor in 2012.
2013.
2013, sorry for my bad memory. So today he will talk about how electron delocalization can help to turn light into electricity in organic and low-dimensional materials. Please join me to welcome Professor Chan.
Well, thanks for the introduction, and thanks for Daniel and John give me that opportunity to kind of give you an update what's happening in my lab. So I think the last time I speak to you was my interview kind of colloquium, which was like 7 years ago. So I guess, it's good that I have that opportunity to kind of tell you what I did. I will not present all the things I did over 7 years, but what we recently come to, in these presentations. So, I am working on this so that's just acknowledgement. So, the funding we get from NSF. So here is my group. So most of the work I present is done by my graduate student, Tika and Bupa. So, and I also have a previous postdoc in my group T, so he also contributed, some of the things that I will present today. Okay, so since I'm interested in these semiconducting materials, so then I have this question here. What is the most widely used semiconductor materials that we have, right? So I assume, of course, most of you know the answer, right? It's silicon, right? So, but silicon, although it has been using in so many different type of devices, it has its own advantages, right? For example, it's kind of expensive to make this kind of silicon device, relatively, right? And then it's kind of brittle and it doesn't really bendable. It's also kind of opaque. When you think about it, it's good for making something like a computer, but maybe for these newer applications, so it has some shortcomings there. So that's why we need new materials for kind of new type of applications. So why we need this new type of material? So of course, one of the things that I was kind of involved in is these new materials for photovoltaics. The reason, it's not like we don't know how to make a solar cell from silicon, but the problem is it's kind of expensive, right? So in order for that to be used by people, then you really need to drive the production cost down. So one of the ideas have been laying over 2 decades or so is that if we have some material that you could dissolve in a solvent and then you can kind of print that on a substrate, then you can make those devices in a really kind of cheap way. It's just like printing your newspaper, right? But instead you are printing your electronic devices. So of course you cannot do this thing with silicon, so that's why we need new materials. So and then of course the other kind of application is this consumer electronic device. These days, we want this kind of device everywhere, and then we want to incorporate them everywhere. So when you think about that, we probably want something that is flexible, right? It won't be break so easily. And then in the near future, so we may have something that is kind of like a transparent devices, right? Just look like a piece of glass when you didn't turn it on, but when you turn it on, the things come up, right? So again, this cannot be done with silicon. So and then of course the other type of application is this medical community, right? They always want to incorporate electronic devices, for example, inside an implant, right? So they can then monitor how well the implantation is working, right? So and then of course you need something that is biocompatible, right? So again, you need new type of semiconductor that other than silicon. So in my lab, so we're working on understanding the physical properties of this new type of semiconducting materials, right? So some of the material we are interested in is these organic semiconductor. So they are semiconductor, but made with some organic molecules, right? So also we are interested in these 2D materials, so such as graphene and this MOS2. And then recently, we also work on this so-called organometal halide perovskite. So they are also semiconducting materials, but they are kind of like an ionic compound. So again, because ionic compound, you can dissolve that in solvent very easily, right? So you can make device out of this material in a relatively cheap way. So it turns out that these materials have a really long carrier lifetime, which enable people to make really efficient solar cell out of it. But I mean, of course, the physics why this material could perform so good is kind of, I mean, still under like investigation. So that's why we are interested in this material. So and then we're also interested in this hybrid interface. So basically just combine these materials together and try to understand the electronic properties at this kind of interface formed by two different types of materials. So what are the new physics, right? So we are physicists, so why does this material different than what we already know? So here is just crystal structure of silicon, right? So usually when you open a solid-state physics textbook, right, the first widely used assumption is we always have these periodic boundary conditions, right? It's almost like we don't know how to deal with this thing if we don't have the periodicity anymore, right? So that's part of the typical assumption, right? We always assume periodic structure. So in this structure, electrons are kind of like waves. And then we also usually assume that we have a relative stable lattice, right? So the atoms or the iron core here doesn't really move, right? And also we also deal with these hard material. What that means is this bonding is relatively strong, so they are not easily distorted by the electronic excitation. However, in this new material, of course, this kind of assumption doesn't really help. So, I mean, the first one is usually we have weak electronic screening. So what that means is, remember, inside solid, you have so many electrons, right? But in the traditional picture, we have this single electron approximation, which no longer hold in these new materials, right? So one of the examples I would talk about is we have these excitons, right? So basically the interaction between the electron and hole. And then because of this weak electronic screening, this kind of interaction become important in this material. So another problem is this material we call soft material. I mean, remember they are made with some really cheap production process, right? So what that means is you make them at really low temperature. So because of that, the bonding between this unit is usually weak. I mean, because you want to dissolve them easily, right? You want to form the crystal at low temperature. So the bonding between these are usually weak. So what happens? So when you excite electron in this material, I mean, you can start to distort the crystal structure. I mean, either it is an atom or individual unit, it can be a molecule, but the idea here is you start to shift the position of these atoms or molecules. So now you have these so-called electron-phonon couplings, right, which can actually affect, I mean, your electronic dynamics. So and then recently, so we look at these ionic semiconductor, right? So one of the problem again, I mean, when you have electric field, so these ions are charged particles, so they can diffuse like crazy. So therefore, these materials usually they are not so stable. I mean, but I mean the question is, of course, how to understand the correlation between these electron and ion motions when both of them are actually moving in, I mean, quite rare. I mean, like you can't just assume one is fixed and just one of them is moving, right? Because now like both of these are moving. So how we understand the properties of this kind of, I mean, behavior. So these are just some of the example of things that we try to understand. So for that particular talk specifically, we want to look at the delocalization of these electronic wave functions, right? So what I meant by this delocalization. So usually, come back to the solid-state physics picture, right? So we always have a periodic crystal, so we form electron inside this solid are what we call something block waves, right? So they are basically like sine and cosine waves, so it's basically distributed in the whole crystal. So again, I mean, this picture come to problems or challenges when we no longer have this periodicity, right? I mean, many things can destroy the periodicity. For example, if you have defect. So even if we have a perfect materials, right? So we still have other type of defects. So for example, we call that dynamic disorder is the electron-phonon interaction that I mentioned earlier. So when you excite electrons, so you will locally distort the crystal. So then you introduce something we call the dynamic defect, right? So this breaks the translational symmetry. So of course, in the other cases, so for example, we study interface. So usually the two materials have different lattice parameter, right? So the lattice cannot match. So in these cases, again, you don't have this perfect periodicity, right? So I mean, of course, electron-electron interaction, just as this electron and hole, so it interact with another localized carrier. So of course, you no longer have these periodic kind of boundary conditions, right? So how do we understand the physics of electrons when we don't have these powerful tools that we always use to understand the solid? So on the other side, I mean, chemists deal with this problem too, but they are usually very good at dealing with individual molecules, right? So they look at the electron orbital of electron of a single atom or a single molecule, right? So in these cases, your electron wave function basically is localized either on an atom or on a molecule, right? It's kind of like the other extreme. So chemists deal with this localized electronic wave function or this orbit, right? So physicists will deal with waves, right? But in between, right? So how we understand the behavior, right? I mean, for the chemist challenge is especially for this localized orbit, it usually don't work well in condensed phase because these electron orbit interact with the environment. And then for these molecular materials, so different molecules interact with each other, right? So how could we understand the interactions? So I mean, in summary, so we kind of have a gap there when the electronic wave function is of the spatial size of this 1 to 10 nanometer around this order of magnitude. Then we don't have much, understanding on how these electronic, state behave in this kind of length scale. So how do we tackle this problem? So in my group, so we use this so-called ultra-fast spectroscopy, right? So it's basically we try to capture the electronic motion in real time. So I mean, just like your fast speed camera, right? But it's working in much higher time resolution. So typically, if we want to study this electron motion, we need something like 10 to the minus 15 to 10 to the minus 9, right? This femtosecond to nanosecond time scale. So what we do is we have these femtosecond laser pulses, right? So we have one pulse that excites the solid, and then another pulse come in later to kind of probe what's happening after the initial excitations, right? So what we call pump-probe experiment. So of course there is different variation for the probe. I mean, you can probe the optical properties, or in our case, we usually do this so-called photoemission. We ionize the excited electron and see what electronic state. I mean, this excited electron come to after some controlled delay time from the pulp, from the pump event, right? So okay, so these are just photoemission spectroscopy we are doing. So we usually have a pump that pumps the electron from this occupied state to unoccupied state. So these are basically the excited electrons, right? So we have a probe coming later to do the photoemission. So we measure the energy and the momentum of these electrons to basically tell, what kind of excited state, the electron is located, after a certain period of time, right? So, here just typical photoemission spectrum. We have intensity and energy. So different energy represent different states, right? So of course you can collect this spectrum at different delay times, and we have this kind of 2D spectrum. So here is time, here is energies, right? So you can look at the dynamics of different excited state as a function of time. So that's the tools that we are using. So that's just some picture of our labs. So these are the photo emission chamber and then the laser setup. So anyway, so come to the science problem, right? So one of the problems we're looking at is the delocalization size of this so-called charge transfer exciton at the interface. So what is that? So what is an exciton? So an exciton basically just an electron and hole pair. They kind of bond by the Coulomb interaction. So usually, I mean for silicon, so this kind of binding is really weak. So it's just few milli eV, so we usually can get those. But for these other materials, like these organic materials or these two-dimensional crystals, so these binding energy can be quite strong, can be anywhere from hundreds of milli eV to 1 eV, right? So they are strong compared to the thermal energies. So therefore, at room temperature, they are kind of bond, right? So now the question is how to separate them, right? Especially for application like solar cell, you absorb the light, you generate this exciton. Now I want my electricity out, right? So how to separate that exciton to produce the electricities, right? So usually people create this interfacial structure, right? So these are what we call the donor material and acceptor material. So donor means that they don't like electron that much. Acceptor means they like electron more, right? What happens is you have an energy offset at the material's interface. So in these cases, electron transfer from one side to the other, hole transfer from here to the other side. So now you have this so-called charge transfer excitons, right? So it charge transfer because it's involved a charge transfer process to make these excitons. So now, these are easier to dissociate, but they are still bond. I mean, usually they still have hundreds of milli eV of binding energies. So still, right? So how we separate this kind of CT excitons at the interface, right? So that's one of the scientific questions we are looking at. So I mean, for organic interface, so I was working on this organic semiconductor for quite a while now. So I mean, for this material interface, usually people think that there is something so-called hot CT state, right? So when you first populate that, so these CT exciton have excess energies, right? So they could dissociate before they relaxed to a lower energy state, right? But I mean, but what is this hot CT state, right? They talk about that, but I mean, physically, how they look like. So one of these ideas, theorists propose is consists of some delocalized wave functions, right? So when your electron and hole are kind of delocalized, the air phase separation between them will increase, right? Due to that spatial delocalization. Then you have a weaker binding energy, then you can separate them easier, right? So I mean, one of the our goal was, I mean, a few years ago, what we tried to do is try to design experiment to observe this delocalized state, right? What is the spatial size? What are the energies, right? So, and how that impact the, charge separation dynamics, right? So that was what was our goal back then. So therefore, I mean, what we did is we do this donor-acceptor interface, right? So we usually try to grow really well-controlled sample. So in that particular experiment, so we grow these C60 molecules onto a single crystal gold surface. So we have really nice epitaxial gold for C60 on gold. So you can see that from the diffraction pattern here. Then we kind of put the other molecules there. So it turns out that for that case, these CMPC molecule kind of standing out, and they kind of form a stack on top of these C60 molecules. So we did some sample characterization, so we know that the molecule oriented like the way that we draw it here. So then we can work on our experiment when we have this well-ordered interface, right? So then we did this pump-up experiment, right? So we have a thin layer of donor here and then a thicker layer of acceptor here. So we use that pump pulse, so which is like 1.7 eV, to pump that top donor layer. So one that excited, exciton created in that donor layer, and then electron transfer to the acceptor layer, right? Then we form these so-called CT excitons, and now we can study the properties of these CT excitons. So, I mean, these are the typical energy level diagrams. So you have this CMPC. So you excite this signet state here. So these CT exciton state have lower energy. So electron like to transfer from one material to the other materials. That case from CMPC to C60. So here is the photoemission spectrum that we collected at different delay times. So time is here, energy is here. So you can see that initially we excite this so-called signet exciton in CMPC, right? Have the highest energies, right? So now these intensity, so the color is the intensity, by the way. So these intensity decay really quick, right? So in about like hundreds of femtoseconds. So what happened is these decay, and then you see these other state got populate, right? So what happened is these signet state transfer the electron to C60 to produce these different CT state, right? So now we can already kind of map out the kind of the band structure for these CT excitons, right? You have different energies and represent different CT exciton with different kind of spatial delocalizations. So here's this control experiment. So if we just have CMPC, the signet state have a really long lifetime. So anyway, so we are interested in this CT state, right? So what's interesting about this experiment is you see this charge transfer. So this disappear in about 100 femtoseconds. And then at a later time, about a few picoseconds, so we saw this signal rises in this lower energy CT state, right? So what happened? Usually what we expect is you see one decay and the other rises, right? But in that case, it seemed that the electron kind of disappeared. I mean, between that 100 femtosecond and then that few picosecond time scale, right? It's disappeared from our pole, and then later it come back up, right? So you see that decay, fast decay here, and then later the signal rises, right? So what we think happening is initially we populate this so-called delocalized CT state, right? So they are delocalized in the sense that the electron kind of farther on average, kind of farther away from the interface. Because now our probe is this so-called photoemission, right? Photoemission is a very surface sensitive technique. So what happening is when it's surface sensitive, when your electron is located farther away from the interface, then your signal get really weak, right? So that's why apparently this signal kind of disappear. But we could kind of, I mean, look at the spectrum more carefully. We can actually see a peak around here, so which kind of fill these two time gap there. So you actually populate this delocalized state, which have the electronic wave function that are farther away from the interface. Then, I mean, of course, these electrons are trapped by the hole, right? So as time move on, it kind of snapping back to the hole, so the whole thing localized. So these stay at lower energy. I mean, of course, because the electron is closer to the hole now, right? You have stronger Coulomb interactions. So we're also interested in measuring the size of this so-called hot CT state, right? So what we did is we basically changes the layer, I mean the C60 layer thickness. So what we did is for thicker films, we always see these rises in the picosecond time scale, right? The localization from this delocalized state to that localized state. So now as we make the C60 layer thinner and thinner, so eventually this delocalized wave function will be in contact with the gold substrate, right? And then if you are in contact with the gold substrate, the gold kind of pull the electron out from the CT state, right? Because gold is actually a really, I mean, it's metal, right? It have a bunch of empty state that can accept the electrons. So therefore, if your thickness is below the delocalization size of that CT excitons, right? So your electron no longer come back to the surface. It's basically transferred to gold, and then the whole signal disappeared, right? So it's actually what we saw here. So for thicker layer, the signal come back, right? So it rises back. from 10 to 4 is all basically the same kind of dynamics. But as you go thinner, so that rise got weaker and weaker until that this 1 or 2 layer, you basically just see the signal decay, right? So what that means is, so below 4, the film is basically thinner than the delocalization size of that hot CT state. So these electrons got snapped out and transferred to gold, right? So I mean, we can also analyze the spectrum more carefully, and we can actually see the sizes for these different states and what are their binding energies. So okay, so it's nice we can obtain this kind of information, right? But then we now move on. So what is the implication of these kind of numbers, right? So I mean, of course, one of these findings we have for that particular interface is that this delocalized state always kind of related to this localized state, and when they localize, it have a huge binding energies, right? 0.5, 0.6 eV, and then it's very hard to dissociate them. Usually, you dissociate them by thermal attenuations, right? So which could take kind of forever. It took nanoseconds, which kind of.
So if you're looking at an exciton,
yeah,
which is a bound state, and there's a relationship between the bound state size and the bound state binding energy.
Yeah, right.
Is that what you're looking at?
Yeah, right.
So can you just, why do you measure this with the fancy high speed timing? If you just measure the exciton spectrum, you know the spectrum, you know the binding energy.
Well, because you don't know how the electron and hole distribute spatially, right? So yeah, I mean, if you assume that it's kind of like a spread out like a sphere, right, then you can kind of relate that with some analytical model. But the problem here, I mean, first, I mean, people don't know whether these so-called hot CT states actually exist, right? So chemists usually what they think is you excite this vibrational hot CT state, so they have some additional vibration associated with that, instead of this spatially delocalized CT state, right? So that excess energy can be in different forms, right? Either vibration or this spatial delocalization. So I guess, I mean, first, I mean,
so
we are more.
I'm making the theory and you're doing the experiment. What is an ML?
What's that?
A capital ML.
Oh, monolayer. So it's like single monolayer of C60.
Which is what?
So it's like one molecules, right? So it's like
in numbers.
0.8 nanometer.
1 nanometer.
Yeah.
Okay.
Okay, so now we observe these different delocalization size, right? What the deal then, right? So I mean, usually, I mean, people assume this hot CT stay localized to this low energy state, right? And the question is how we separate them. So one way that people propose is to separate them in this hot state before it localized, but it kind of happened very fast, right? Within a couple of picoseconds, right? So can we actually achieve that, right? One of the questions. And then the other question is, I mean, of course, I mean, can we actually make another type of interfacial structure that we can actually allow this bound state to dissociate directly to this hot state, right? So that's basically, I mean, two of our goals, right? Whether we could extract that from hot CT state or whether we can tune the interfacial structure so that it can actually go energy uphill instead of energy downhill. So that I will talk about in a minute. So anyway, so we are also interested in whether this free carrier actually generated from this charge transfer exciton. So it's a little bit sidetracked here. So actually, I mean, we collaborate with Judy's group. So her group is very good in making these graphene field effect transistors. So it turns out that they are really good light sensor. So what we do is we use those sensors to basically probe the free carrier generated by these charge transfer excitons. So I won't go into the details here, but here the probe is a little bit different. We probe the electrical signal, so we don't have as good as time resolution, but we can probe this free carrier quite exclusively because you can only probe free carrier by this kind of electrical circuit. So we grow the same type of sample, right? Donor-acceptor interface, but it's on graphene instead of this gold substrate. So then we measure the number of carriers transferred into the graphene. It's basically generated by this, charge separation, right? So here is some of these dynamics we obtained. So we basically change the C60 layer thickness again, right? And then we obtain the rise time of the signal. It's basically how fast we detect this free carrier. So of course, for thicker layer, we expect that to be later, right? These excitons need to be separated, and then electron need to transport to graphene. And then we measure that as a function of thickness. So you see that for very thin film, we don't have the time resolution to probe those. It's basically below the time resolution of our oscilloscope. So it's basically limited by the oscilloscope. But after we go to these 5 or 6 nanometer, then the rise time actually have a jump, right? So from these very fast and then to these slower ones. So remember I say this hot city state is about 4 nanometer, right? It's kind of seem to be related to that. So what we think happening is for very thin layer, so we have this delocalized state, right? So this graphene kind of pull the electron out from this delocalized state before it have the chance to kind of snap back to the hole. So that's why you have this extremely efficient dissociation. But for this thicker one, I mean, these electrons have time to localize back, right? So then it's very difficult to dissociate these bond charges. So that's why your time, the rise time, certainly jump up by 3 to 4 nanoseconds. It's basically the time taken for these electrons to escape from the bonding from the hole, I mean, in the CMPC layer. So and now, of course, it keeps increasing, which is the diffusion of the electron to the graphene layer. So we also did the temperature dependencies. So this delocalized state is basically doesn't depend on temperature. Localized one, strong temperature dependence, probably due to some thermal activated process, right? So now, I mean, of course, you can kind of engineer another type of acceptor within this kind of distance from the interface, right? But it's difficult to do it that way. So the other way to extract that, right, so is what I mentioned earlier, right? Can we have this bond state actually want to go to this delocalized state? So that's the question, does this hot city state always kind of localize to some smaller one, right? So that's why I come to this other project, we try to tune the interfacial structure, right, to see if we can achieve something we call a spontaneous exciton dissociation. So in the earlier interface, we have this hole basically delocalized parallel to the interface. So, right? So even that it delocalized, the distance is still quite close to the electron, right? So we just think of, can we change the stacking of this orbit a little bit so we can have this hole and electron kind of delocalized in different directions, right? So in that way, if this state can be delocalized, then, I mean, it automatically, you kind of force the spatial distance between them farther away from each other, right? So you kind of weaken the exciton binding. So what we thought, you probably could generate free carrier easily with this kind of structure. So that's why we do this experiment here. But actually, we kind of surprising from what we saw. So what we did is, again, we excite this donor acceptor, right? So in that case here, we excite both, actually, but we can study the electron transfer to the top, like FZMPC layer, right, which is an acceptor. So we're probing the electron in this charge transfer exciton. So the main difference for that versus the previous one is that we first excite this lower energy CT state, and then later the energy actually goes up, I mean, instead of going down. I mean, it's kind of like these energy uphill reactions, right? But it's kind of go up instantaneously in a very fast time scale, right? So it's actually quite interesting, like what happening, right? What happening to that interface? Like you can go up in energy instead of going down in energy, because every time we know that it's always go to lower energy state, right? But it kind of, going up here instead. So what happening? I mean, it's easier to see it in the spectrum. So the lower energy state go down, and then the hot state go up, right? So energy level diagrams is actually these so-called CS state even have higher energy than the initial syngness state, right? So we kind of driving somehow these energy uphill reactions, right? So what's happening, and it occurs really fast, right? If it's slow enough, so okay, it could be some kind of thermal attenuated behavior, but it's actually occur really fast rate. So what's happening? I mean, of course, to measure that rate, we can again vary the thickness of this layer, and then we kind of probe the electron at the surface. We can see how fast the electron come up to the surface, which is the transport time here. We can also see how fast the spectrum shift in energies, right? So for that shift in energy is actually the actual energy uphill process, right? So we can measure that as a function of thickness too. So of course for thicker film, we can't really see this bound-CT state, right? So that's why the data kind of stop here. So anyway, so these are like the 10 femtosecond, 20 femtosecond time scale, right? So it's very fast. Why would I say it's fast? Because if you use the typical like thermal attenuated rate, right? These exponential terms minus the attenuation energy divided by kBt, right? Then you get a rate about like 10 to the 9, so nanoseconds, right? So these kind of like 2 to 3 orders of magnitude faster than typical thermal attenuated rate, right? So what happened, right? So what happened is that we think that the actual barrier, we cannot use that delta E, right? So if you go to just basic thermodynamics, you know there's something called free energy, which accounts for the entropy. But usually, I mean, people working in this area, I mean, I realize that, but sometimes it's overlooked the effect because usually they think about two molecules, you can't have the entropy changes too much, right? Because no matter it's hot or cold, I mean, you still have just two molecules. You cannot really drastically increase the number of configurations, right? So what do I mean by this entropy? It's just some thermodynamics, right? So entropy is basically the number of configuration you could have if I give you certain amount of energy, right? So how many ways you could arrange the system, right, to have that same energies. So usually, I mean, people like to write down this thermal attenuated rate, right? So they have this delta E there. You have this kind of term because for an energy uphill reaction, you took some energy from the environment to your systems, right? So of course, if you do that, you kind of decrease the entropy of your environment, right? So that's why these things don't happen so often, right? Because, I mean, you need to wait for the instant when the system like to take up that amount of energy, which reduces the entropy of your environment, right? But you can actually compensate for that if your entropy of your system is increased by the energy transfer process, right? When you have energy transfer from the environment to systems. So that's the delta S we have here, right? You can have this energy loss from the environment compensated by the energy gain in the system. So in that case, the charge transfer state, right? So why we think that delocalized state have a larger entropy? I mean, if you think about the electronic wave functions, I mean, basically, delocalized state involve more molecules, right? So, I mean, then you have more combination to kind of arrange the electrons, right? But still have the same energies, right? So we can calculate something called the density of state, basically the number of state per unit energies, I mean, for that particular interface, and compare that function for different interface, right? So we set up this kind of model Hamiltonian. I don't go into the details, but we basically use these two electron wave functions. We assume the electron is at a certain molecule in the acceptor and the hole is at a certain molecule of the donor. And then we have these Coulomb interaction terms here, depends on the distance between the electron and hole, right? And then we have these electron hoppings in the acceptor and the hole hoppings in the donors. So, I mean, we can write down this Hamiltonian and diagonalize that to get all the eigenenergies and eigenstate, right? Then we can count the number of state, I mean, in each of these energy being and kind of basically kind the omega in the entropy function, right? So here is all the eigenstate that we kind of find. So these are energies. So each of these dots is an eigenstate. And then these are the average electron hole distance, okay? So now these states are kind of clustered around 0 eV, right, which is basically the band-like state. I mean, if you have a delocalized electron, you form this band, right? So basically the width of this band is the electronic couplings between different sites. And then of course we have a tail here, so which correspond to the bond CT state. So these states have lower energy. It's exactly the Coulomb interaction terms, right? So as your distance between the electron and hole come closer, your binding energy become bigger, right? So now we have these, then we can count the number of dots in each of these energy interval. We can have this kind of density of state function, right? So of course we can also look at the spatial distribution of the electron and hole for each of these individual states too. So I kind of pulled two examples here for these two different interfaces, right? So the idea here is these states usually have a lower density of state for this tightly bound state because you really don't have much possibility to have this bond state, right? Because you need to have the electron and hole right at the interface. When they start to delocalize, automatically they are farther away from the interface and weaker binding. So versus in that case, I mean, the electron and hole kind of falls to the interface due to that structure of the crystals, right? So your hole is kind of always kind of gliding parallel to the interface. So that's why you could have more different combinations that you have. You have your hole really close to the interface, and this, I mean, many possibilities for this tightly bound state. So to read this graph, so basically if we want to look at this energy uphill reaction, right? Basically we want to go from lower energy state to higher energy state 1. So we basically compare the gain in entropy, right, delta E, and then the gain in entropy, right? So if the gain in entropy win, then we can have this uphill process happens like instantaneously, right? They want to go to that uphill directions, right? But on the other way, if we have that entropy contribution weak, right, then we can actually have this exciton cooling. So that's what we think is happening. So for that FCN, PCCN, PC interface, you can see that the entropy gain is more rapid compared to delta E, right? So in that graph here, so the slope is flatter. So versus that for the other interface, the slope is steeper, so the entropy gain is kind of faster, than the energy gain, the free energy gain due to the entropy. So these lines are just of the calculated line when delta E is exactly equals to T delta S. Like how does that look like on the graphs here? So we can kind of use the entropy idea, to explain why you have this kind of, instantaneous kind of separation of these bond excitons. So of course that could be useful. That means that you can kind of engineer your orientation of these electronic wave functions, right, to promote, this kind of dissociation of these bond excitons. So here I'd just like to talk about how people think about that commonly over the last decade and what we think is different in our current picture. So usually people think about you populate these hot city state, but the idea is that these hot city state always kind of relax to this cold city state in very fast time scale, right? So therefore they always look at the competition between these different pathways, right? The separation of this hot city exciton and then the separation of this cold city exciton. So we think that that picture is not that right, and indeed it leads to many different arguments. Some results seem to show that the cold pathway is just the only pathway that could be important. And some work, they observe this CT state, and they say that the hot, they observe basically very fast dissociation of this exciton. Then they think that hot pathway is that important. But I think that this picture is not quite accurate in the sense that it's always assumed that go down here. But what we think is, depends on the configuration of your interface, right? So you could have some interface that really kind of utilize the entropy effect, right? So which allow this cold state kind of go to this separated state simultaneously, versus, you could have these different interface in which the entropy effect is weaker, then you have this delocalized state actually localized, become this bond CT state. So that's one of the conclusions we have. So I think I don't have much time left, but I will try to finish that in like 3 to 5 minutes. Then we can have the Q&A session. So, and then the other thing that we are interested about is these organic 2D interfaces. So usually, I mean, again, you excite this electron hole pair in one of these material, and then you have this electron transfer, and then generate these bond excitons, right? So this area, I mean, this material system is a little bit newer. I mean, in the sense that 2D materials is newer, so people didn't have much knowledge about how this thing have occurred yet. But our focus here, I mean, usually if you look at the literature over the last few years, I mean, what they measure is they often measure the initial charge transfer rate. So usually they get some weight, they see the charge transfer, then they think that, okay, so that interface is good. I can transfer electrons from one material to the other materials. But our point here is, even you have this electron transfer, right? So the electron hole might still bond together at the interface. And then whether they separate or not, it's not like you can't take for granted. I mean, even you have the initial charge transfer, maybe they won't separate. And then, indeed, they could even recombine quickly, right? The electron can go back to the original materials. So that's why we're interested in this molecular and 2D system, that actually what we observed. So for this bulk MOS2, so basically many MOS2 layers, right? So we actually don't see these charge transfer excitons separate. But instead, the electron actually go back to the organic layer and form these so-called triplet excitons. But versus for the monolayer, so we see that the electron and hole actually separate on the interface. So I will skip all the experimental details if you don't mind. Just believe the conclusion here. So what we think is happening is, I mean, for the monolayer, CMPC monolayer MOS2 sample, somehow we have very flat band here. So the band didn't bend much. So, but versus the bulk CMPC, we have this sharp bending here. So basically, we see that the energy level kind of decrease as we grow thicker and thicker layers. So these, by the way, we actually measure it. So we measure how the energy level changes as a function of thickness. So then, for this, because of this flatter band, so actually look at the diagram on the bottom here. So what we think is we form this CT exciton, so the electron and hole, they can move away rather easily, I mean, without much problem because of this flatter energy landscape. But for the other interface, we have this huge band bending. So what happens is, I mean, if you have this kind of band bending, so electron like to go that way and hole like to go that way, right? So unfortunately for this CMPC, the hole is on that CMPC, right? So it kind of trapped at the interface. And then more unfortunately, so for bulk MOS2, the people know that the spin lifetime is shorter, so the spin can kind of flip quite easily in bulk MOS2 compared to monolayer MOS2. So now the hole is kind of stuck and the electron spin can flip. And then now the electron can actually go back to the molecule to form this so-called triplet exciton. And another unfortunate combination is because for these organic molecules, the exchange interaction is quite strong. So you have a hole there, which is basically you have two more energy level. I say hole means that instead of one electron, I mean instead of two electrons, you have one electron and one hole, right? So that electron and the excited electron, if they have the same spin, you have a much lower energies versus they have opposite spin, right? Singlet and triplet. So then, I mean, because of that, so if you have spin flipping, then these electrons can go back to form this lower energy exciton, so which is actually what happened, then you form this triplet state. So of course, practically, unless you really like these triplet excitons, right? So otherwise, if you use that for solar cell, then it's not good, right? If you use that for photodetector, it's no good because you don't produce current, right? You still produce this bound exciton. But of course, in some other application, like these light-emitting applications, right? So they usually want exciton that have really long lifetime. So in that case, you want to form a lot of these triplet excitons because they cannot recombine, I mean, unless you flip the spin again, right? So in that cases, I mean, this kind of interface might be more, I mean, good for those applications. So anyway, so that's my summary. So we basically try to understand these new semiconducting materials. So in this particular, I mean, presentation, I kind of go through some of the work on this so-called CT exciton, and I mean how we could understand the dissociation of this bond, kind of bond state, right? So we talk about that could affect by the electron delocalization side. Could also affect by the structure, right? The structure and anisotropy. And then, of course, the entropy and energy, potential energy lengths get kind of important too, right? So I guess I will stop it here, so, and then open for questions. So thank you for your attention.
Okay, you go first.
As I understood it, your experimental data showed an unexpected increase in the energy as a function of time, and you expect the energy to decrease.
Right, yeah.
And then that's what the entropy argument is for.
Right, yeah.
Is to say if your energy changes at fixed free energy, you have to change the entropy.
Right, yeah, right.
All right, well, I mean, if it's in equilibrium, you're right.
Right.
And you don't have to argue it. It's just,
right.
you're done.
Right.
What makes you think it's in equilibrium?
Well, I mean, it's...
Wait, because you have all these long, measuring things on a very short time scale.
Yeah, right.
You have this very long distance propagations. It seems to be interacting very weakly. And you cited a number, I thought.
So the weight, right? Yeah, right.
Nanoseconds.
Right.
So what makes you think equilibrium is relevant?
Well, so first of all, the Arrhenius rate is kind of from some kinetic theory, right? So I mean...
Well, it's 1,000 times longer than your picosecond.
Yes, so that's why we think that first, I mean, I call that time is that because you could say that it's just normal thermal iterated process, right? But that time scale is so different, like it cannot be like a usual thermal iterated process.
From your data itself, what you can measure
is the energy of the electron.
Instead of this is just a sort of typical non-equilibrium fluctuation.
Well, I don't call it fluctuation because fluctuation it could come back to the bound state, right? But we actually see that go to that higher energy state for longer time. I mean, of course, kinetically, I mean, we need some more involved model to actually understand how could this, I mean, relative bound state can kinetically go to this, I mean, more charge separated state, right? So in that case, I mean, it's more difficult to kind of simulate, I mean, because you really need to see how this electronic state, I mean, basically solving the time-dependent Schrödinger equations, right, for these very large systems. So I guess I don't really have a good answer for that, but I mean, for experiment-wise, I mean, we observe these energy uphill reactions, right? So it's not some fluctuation; it's just stay there, right? It don't go back. I mean, of course, I mean, it's happening. Then we want to check, right? So if you just look at it energetically, I mean, it cannot happen that way. I mean, because I mean, if you just look at that delta E, I mean, no way you could happen that way. Then, I mean, we kind of think that what other driving force can allow that to happen, right? So one of them is this entropy driving force. Of course, one of these important things we try to point out in our our work is that this entropy force depends on your structure too, because the structure limits how your electron can spread spatially. So it basically affects how your delta S changes as a function of energies, right? So that's why in one interface we see that the reaction go to one direction, for the other one, go to the uphill directions, right? So I guess my bottom line is, if it's not thermodynamically possible, I don't think we can observe these uphill reactions, right? Unless it's just some fluctuation, but we don't think it's some kind of statistical fluctuation. Because you actually have to.
Quantum mechanics does not obey the rules of thermodynamics. So the interesting reason to ask the question is, maybe you could build a Maxwell demon. It's not crazy. People observe.
Okay.
People observe wrong thermodynamics in sufficiently small microsystems.
Well, we are measuring an ensemble average, so where we are measuring like
that's why you could
thousands, hundreds.
Make a lot of money off it.
So I assume you're talking about the fluctuation for a particular electron-hole pairs, right?
No, you said the time-dependent Schrodinger equation, but the time-dependent density matrix equation for interacting systems does not have the entropy always decreasing.
Yeah, right.
Always increasing. The entropy can decrease if you have a smaller system inside a larger one.
Yes.
Classical thermodynamics says it can't happen.
But one thing you couldn't really model by this is the interaction with the environment, right? If you have a closed system, you can solve the time-dependent Schrodinger equation nicely, but if you have interaction environment, then they have this so-called defacing kind of thing, right? So which is kind of, ongoing thing that those theorists working on. I don't know much detail, but I thought it's quite difficult problem to tackle.
Well, since our speaker will be here for an extended time, I guess we can carry over the conversation later. Maybe we have time for one other short question. There is one. If not, I will save my question too. So let's thank our speaker again.
Thank you.